What is good? Happy Sunday, folks. Today we're going to be taking a look at x86 assembly with some of that IA32 syntax. We're going to be using godbolt, and we are going to have to use the terminal to do some compiling, check the differences real quick, get our compilation down for the purposes that we need, and then we'll take a look at if statements, while loops, for loops is the same thing, switch statements, and that's it. Basically 3 constructs today, and in the future we will take a look at some actual tools, but for now we'll just be using object dump and xxd. So let us get to it. Alright, so let's set the scene. We have 3 files we'll be looking at. One that does an if statement with some file input and a global variable. We have a while and a for loop that has a while statement, a while loop with an if statement, and a for loop with an if statement. They should be identical, and we'll confirm that. There's also a directory looking features, so we'll kind of do some OS exploring. And finally, we have a switch statement, which is going to take a look at a string, do some user input, so we'll see some of that. Check the contents of the string. Unfortunately, we have to go through the entire string, try and determine if it's an int, a float, or just a bunch of non-numerics, and we will then put a little switch here, just a 3 case plus a default, and go through that. This is obviously not great because there are going to be strings with floats or decimals in there, but this is just an example. Now let's look at the compiling settings that we'll be messing around with. Alright, so let's get started. We're back in godbolt. We have 3 files in godbolt, 3 compilers, and each file is compiled independently. So we have a total of 12 files open. Godbolt is sick, and you can, highlight over the areas that you want to look at. Big up godbolt. We'll also be using GCC here, go through the man to make sure that we can find what we're looking for. And we will compile with the following flags. M32 for all of them. That's just going to put us in the IA32 syntax. So we're going to be stuck with the 32 length registers portions. So we're starting with an E. That's really makes no difference, but it kind of simplifies things. It doesn't make a difference, but that's what we're doing for convention. The fpi flag over here, that's going to force a position independent executable. As far as I understand, without this flag, the memory of things in the program are predefined in the linking portion of the compilation process. So if you're a malicious actor, you could sort of know where things would be without actually running the program. And this is going to allow you to have a position independent executable. So these things are not defined necessarily by the linking table. It lets something else, maybe the operating system, do some of that definition. I'll double check that and we'll explain it once I'm showing everything in the terminal. fnopy just turns that feature off. There is a slight difference between fnopy and no flag at all. So the default is not fpi or fnopy, somewhere in the middle. Let's take a further look at this with the man and hex dump, and then we'll compare the outputs. There is a slight difference for some reason between what GCC on the terminal outputs and GCC and godbolt, even though my GCC version should be consistent here. It looks like we're a little bit behind. All right. So it's ill-advised to update GCC to the newest version. There might be conflicts, and I'm not ready to determine what conflicts may arise from doing that. So let's just quickly compare these 2 object dumps from 13.2 and 11.4. There's some slight differences here. Actually, there's more differences in between the outputs of compilation. If I go to 11.4, we still have these GS and DS portions that seem to point to segments of memory. And it looks like the object dumped from GCC in the Ubuntu terminal. So I think what we're seeing is that in godbolt, the returns of the functions that are called are abstracted inside the function potentially. And in the compiler on GCC on Ubuntu, it looks like it does the returns of the function for us, perhaps. So every time we call a function, it seems to do something with the EX and push it on top of the stack. And it does seem to access these memory segments, I suppose. This is a segment register, and that doesn't seem to be visible here, but I think that's specific to a function being called and going to these segments. So there are some slight differences. That's independent of the compiler, though. We did not see too many differences when updating or going to or downgrading to a different compiler, but there are some slight output differences. Other than that, though, everything's the same, and that shouldn't affect the analysis of the assembly. All right, so understanding the GCC flags, we have a couple options here. We have GPT, we have Gemini, and we have the man. The man is pretty good. It's missing some stuff. It doesn't have the fno command. I piped less, so I did GCC less so I can search here. And as you'll see, fno pi, it's not in there. fpi is, some things are in there, some things aren't. I'm getting pretty good results from Gemini. I like the searching explanations. It does seem to hallucinate a little more, but when it comes to searching things that are on the internet, it does give, I think, better answers. So we can compare. This is just one example, obviously, so you're gonna have to take my word for it, but this is GPT's response. A little short, kind of convoluted, not that great. Gemini's response, a little more in depth, a little less complicated. I think it's better. Those are our options. I recommend you go through, if you don't understand these, and look those up. Did a pretty good job of explaining for me. M32 is going to put everything in 32-bit format, so all the ints and everything is going to be 32 bits. That's just going to simplify things, as I explained before. The fpi is going to put us in the program independent, what did it say? Program independent executable format, which is the recommended way to do things so that the memory locations aren't predefined in the linking process. And the NoPy is the fNoPy is just gonna turn that off. So that's what we're using. Let's go ahead and look at these code constructs. All right, so if statements. I think the main thing to consider when looking for an if statement is we want one decision being made, no return back to the place where the decision was being made in an isolated if statement. If the if statement is inside a loop, we might return back to that section that contained the if statement, but the if statement itself, you will see a comparison of some sort, and you can see there's two if statements, and we have two comparisons here. A comparing if they are not equal to 0, this variable, and a test of EAX and EAX, which in this case is going to do an AND operation on EAX and EAX and return the result. We're looking for a 0 result here. So we have one comparison that jumps to one location, another comparison that jumps to the same location. So with just the assembly, we can then go to the location that things are jumped to. We can see that there's no additional comparisons. So we have a comparison and then we move on. And that's a pretty good sign that it's a if statement and these are going to the same location. So we can maybe assume that the if statement contains two conditionals. And for the second if statement, we see that there's only one comparison. We go to L4, we don't return, we move on. We can guess that there's another comparison, no return back to the comparison check. Pretty safe to assume that that's also an if statement. When we go past these, if this doesn't check, we continue. If this is less than, we continue, and then something else happens, and we still do not return back. So it's pretty safe to assume that since there is a single comparison and no return back to where the comparison was made, the only code construct that really performs in that manner is the if statement. So we can be pretty safe in looking at this as some sort of if statement. And so let's wrap things up and take a quick look at the O3 flag for the if statement. So again, this code is basically just checking that if the hour is between midnight and 6 p.m., then that's a bad time. You shouldn't be, it's an inappropriate working hour. If it's after 6 a.m. and before midnight, that's a good time. So that's what it does. And we can see here that that's really only one comparison that you need. Really, we're checking that if it's after 6 a.m., it's a good time. Since time is cyclical, in this case, for the hour is cyclical. So there should be no negatives, and it should really only check if the value is greater than 5. If the value is greater than 5, we go to the L2 section, and the L2 section here checks the good time string, or uses the good time string, and that this is an appropriate working hour string. So instead of having two conditionals, both of these, we only really needed one, and the O3 optimization took advantage of that, which is pretty cool. It also shrinks things up pretty significantly. So for the purpose of analysis, you may benefit from this, but I have seen this makes things pretty convoluted, and I think we'll see that. So let's move on to the while loop. All right, so let's take a look at the code for the while loop that we have here. Maybe this will be a little bit easier to see. We have actually a few code constructs. We have an if statement, a while loop, and a for loop. And what this code is trying to do is open the current working directory, count the files in the directory, and count the files in the directory, then close the directory. We're checking if it's a regular file. That's what this DT-reg does. This was suggested by either Gemini or GPT. Don't need that, really. I would be satisfied counting any file in there, but I'm not even entirely sure what a regular file is. But that's what it's doing. So we want to look for an if statement. We want to look for a while loop. and we want to look for a for loop. Now, normally we don't have the code available to us, but with godbolt, this is going to help us kind of see how things are going, make things easier to learn. But we can start just looking at the assembly and see if we can understand anything. So with just the terminal, we can try and do a little gcc-m32-fno -pi, just so that we can see where things are going a little bit easier. And we can do a -o while for fno pi, and we want to run the while for.c file. All right, so with the fno pi, we do have this warning about the relocation, because the location that the linker decides and the actual location vary. So we do have to do some relocation since we don't have the fpi feature of not needing to know the exact location. So now we can do an obj dump with -m and then intel and then intel and then -d for the disassemble, and we want to disassemble while for underscore fno. Actually, we don't even want to obj dump right now. Oh yeah, we do. So here we're in the main here, and this is normally all you would have available to you. Anyway, so we can go here. Looks like we're pushing something up here. This is -16. So it looks like we're setting things up here. We're loading 0 into these two variables, adding to the stack here. This is setting up the stack. So we're going to set up 20 bytes on the stack, and then we're going to put another 16. Then we're going to move EAX in here. We're going to do a comparison. So now we have a comparison. And if they're not equal, we jump to 12.4e, which is here. We go to 12.4e, we put some more space on the stack, and it looks like we push some value here onto the top of the stack, and then we call a function. So I would imagine that the function is going to use that value. And then once we're done, we clean up. We'll have the caller clean up the stack here. And then we continue. We put EAX on the stack, and we do another comparison. Then if they're not equal, we jump to 12.3f, which is here. So that is another moving of a value into EAX, moving of a smaller value into EAX, the rear portion of it. And then we're doing a comparison with that rear portion in the AL with the value 8. And then if they're not equal, we're going to jump again to 12.4e, which is here. If they were equal, we would have added a value 1. And that's a good piece of information. So at some point, if the loop iterates such that it's equal, we add 1. Otherwise, we don't, and we add to the stack, and we push another value onto the stack, which is 12.4e, which is where we were up here. So we come back to the beginning of the loop, or we come back to this position. I guess we don't know it's a loop. At 12.4e, we push another value, we call a function at 12.5.5, which is in here. So this is right before this is the function then. So we then go in, we add, we clean up the stack a little bit, we move another value, we do another comparison. If they're not equal, we go back to 3f, we move a value, we do another comparison, then we go back to 4e if they're not equal, or we add 1, and if they're 1, we then continue the loop again. If they're not, then we go to 4e and we don't add 1. So it looks like we're doing some sort of comparison. Then we do another comparison, and this second comparison we never jump to. So we don't jump to 5.4. And since we have a call, we have a function that we don't jump back to that makes a jump, it looks like there's one comparison and we don't return to it. So we can be pretty safe to guess that this is an if statement. So it looks like there's an if statement inside of a loop. And if some value is equal, we add 1. And that is pretty much what we can determine from this loop section. So we've done some analysis. Sorry, that was kind of long and boring. This is also potentially long and boring. But to further understand, we can open up xxd here as we have done. We can wquit, and that's the command that I run. I pipe less so that we can kind of scroll better and do some searching. So we should be able to search 2008. It's not going to find it because it's looking inside. It searches in the text portion. So we have the string period, which is going to be everywhere. But we can, in this case, I guess we'll continue assuming we don't know where things are. So we want to see what 2008 corresponds to. So we're going to scroll down to 2000 here, and here we are at 2000. This is position 0, and this is position position 1, 2 digits at a time. So this will go from 0 to 1. This will go from 1 to 2. I'm sorry, 1 to 2, right? So we have 1, 2, 3. This will go from 2 to 3. This will go from 3 to 5. So 1, 3, 5, 9. So 2008 would be, let me see, 1, 3, 5, 7, 9 here. So 8 would be 2E. And if we check the ASCII table, 2E does indeed correspond with the period. And if we go to godbolt, we will see that we want to open dir period. So that string is what's the first thing that's getting pushed, and we see that here. Similarly, we can check 2000A. A is the number 10 in decimal, so that is 72. I'm sorry, this is actually, yeah, so this is in decimal. So we got 1, 3, 5, 7, 9. 10 is going to correspond to 6F, and 6F is the letter O. And I believe we should see the string open dir as we do here, and it's going to push that value, O. It's going to be a pointer to the O portion, and that's going to be handled to take the whole memory. Usually a string is a pointer to the first location in memory if it's a continuous block, so that does correspond. That does line up with what we're looking at. So I don't want to drag on this portion because it's kind of, well, it's definitely interesting, but first thing we want to do is object dump, look at the code, and then we can do xxd to look for certain strings. Maybe we want to search for the word malware. Well, it's not in there, thank God. So this is definitely not malware then, because it doesn't have the word malware in it. Maybe. Okay, so this video is getting a little lengthy, so let's, the while loop. So the while loop, you can see, and the for loop, because they're exactly the same, and we can see that right here. This is the while loop, and this is the for loop, so we'll quickly go through. In a loop, you have a condition that you check. Based on that condition, you make a decision, go to the decision location, and we notice that we jump back to the location that the original decision was made. And that gives us an idea that we're making a decision, and we're going back to that decision. We're making repeated decisions. And we'll notice that if the decision condition is not met, we continue, then we still end up back in here. That's just a function of the fact that this is has an if statement in there, and we are making two decisions. But generally, loops, you make a decision, you do something, and you go back and you make another decision. And that decision is usually going to be some sort of arithmetic comparison or something of that nature. And if it's not met, you are done making decisions and you continue on to something else. For the if statement, you make one decision and you don't go back. You don't go back to where the decision was made. So finally, we can see here that for this while loop, we add some space on the stack pointer, we push a value, and we call the function, and then we clean up the stack afterwards. After we called the function, that's just the convention for this. We clean up the stack for whatever the function was using. We clean that up, and then we put a value that was in EAX, probably from the readAdder function, because EAX is the return register. We put that in this spot here on memory. We put 0 in this spot here on memory. We compare the value from EAX to 0. If the decision, then we make a decision on those. If they're not equal, we jump to L5 and we continue. As you can see here, all that is doing is reading an address. If it's not equal to null, we continue. Then once we're in here, we have another if statement because we have a single comparison. We make a decision and then we move on. So in this case, we make a comparison to this portion of the register. The AL is a subset portion of the register. We compare that to 8, which I assume is the code for DT-reg or something like that. And if they're not equal, we jump back to L4 and we don't add a value. If they are equal, we add 1 and we continue in. Now, similarly, the next loop, the same amount of space, we rewind the adder, the directory, which means we rewind the directory stream back to where we were, because this is going to stream through the locations in the directory. We just rewind it back. Then we clean up the stack because we called a function. We add that 12 again. We do the same exact thing except at a slightly different memory location. We call that function again. We go ahead and we move to L6. L6 is down here, and you'll notice that L6 is going to look almost identical to what we were having before. We go through. If it's not equal, we jump to L8, which is similar to jumping to L5. You can see that they're identical. Then we go back to L7. If they are not equal, we skip that part and we jump to L7. Then we, instead of jumping into L4 at a certain location, we just copied this into here. So you can see that the code itself is exactly the same. Here it's a little bit separated because we have the while loop and the for loop directly in line with each other, but loops are loops. So we have loops and if statement. If statement, if there's a decision made and we don't return back to the portion where the decision was made, probably an if statement. Loops, if a decision is made, we go somewhere or we do something and then we return back to the code block where the decision was made, probably in a loop. Very simple. And a switch statement, we don't have time for it in this video, but we'll do switch statements and a few other constructs next with more focus on other tools we can use for static analysis, which is what this is. All right, let's wrap things up. We took a look at some compiler options, specifically fnopy and fpy, as well as the M32 option and the O3 option slightly. Just want to get our feet wet. We took a look at godbolt. We took a look at GCC. We took a look at XXD or double XD. We looked at two code constructs, if statements and loops. We found that for loops and while loops look essentially identical. And we will take a look at switch statements next. This is the first video in the portion of videos where we're going to just take a quick look at some static analysis techniques. And I will go into static analysis in the next video with a proper explanation and introduction. So I appreciate y'all. Hope you have a fantastic Sunday. Be easy. Peace.